Okay, what is this open form actually? See, the open form is a free, a powerful, open source, and versatile computational fluid dynamics software. The one particular thing what most of us will be thinking is it doesn't have any graphical user interface, GUI, what we call. But still, it is solver is so powerful that it can focus on any kind of physics problem or set of equations, whether it can be simple as a continuity equation or your modified Navier-Stokes equations or solving your energy equations. What it follows actually, it follows a very simple numerical methods. Okay. Now, what it is actually, see, if you look at it actually, it's a command driven. That means I have to go maybe get all the things done from your terminal. Okay. Almost every command will be passed through the terminal because as I told that open form doesn't have any GUI and will be modify all the files using a simple text edit file. So I am going to use gedit file in the Ubuntu. Okay. Now, say for example, if you go back to your folder, as I told, so I told that I can import all the tutorial files in the open form directory in a single command. Using a single command, I can do that. So before that, what we'll do, we have to go to that particular folder. Say for example, in the little bit of simple Linux commands you have to do. Okay. Say for example, if I want to go to a particular folder, I have to put cd. Okay. So I have a folder called Dropbox. Okay. I go to that particular thing. So if I want to check what are the folders in that, just I'm going to type ls. Okay. Here I have open form, cd, open form. Just I'm going there. Look at this. I am in the folder cd open form. So there, so if I type ls, so I have so many things and all. So I have two folders, turbine and tutorials. Okay. PD tutorials. Okay. If I look at it, look at this. See, these are the open form tutorials which I have imported from your open form directory after installation. Okay. To do this, what we have to do? See, we have to import all these things. How can I do this particular thing? Simple command. See, go to your directory where you want to install, where you want to import it. Okay. Use the simple command cp space. If you want, you can note down -r. Okay. Space. So I'm going to run that particular thing, and so you have to start with a dollar. Dollar means that particular parent directory. Okay. The parent directory is, it is actually home tutorials. Home _ tutorials. Everything is capital. Okay. Home tutorials. And 2. Okay. 2, for example, I want to give, it has to be some examples. Okay. So now if I run this, so I'm going to copy from home tutorials to the folder which I am creating called as examples. Okay. You are copying all the files from home tutorials to a folder called examples in your current working directory, in your current working folder. Just press enter, everything gets copied. That means all the combustion folder, electromagnetics folder, Lagrangian folder, stress analysis folder, compressible, mesh, discrete method, heat transfer, multiphysics, basic, incompressible, resources, DNS, all the folders, and couple of files are there, all clean, all run, all test, some 3 files. All these 3 files and all these folders will be copied from there to your folder. Need not run every time. Say for example, you can just go to the incompressible and see where the lid driven cavity problem is there. So all the examples are imported to your folders. Simple, run this command and you will get it. So now I have put tutorial, instead of examples, I have put tutorials. So in my tutorial folder, everything is here. So this is what I have. So if I go to OpenFOAM, tutorials, you see everything. Basic, combustion, compressible, discrete method, DNS, electromagnetics, everything. It will take a couple of minutes, around 4 to 5 minutes it will take. And everything will be, all the folders are copied. Then these 3 files will be copied. So this is what you are copied. So this is what you are going to get if you run that particular command. Okay. Now, say I want to go to lid-driven cavity problem. Okay, lid-driven cavity problem. So now, as I told, if you go back and see in your OpenFOAM, it was telling you that you have to go to, okay, you have to go to that particular PITZ daily something they showed. No, I'll go to that. Okay, OpenFOAM download. OpenFOAM Ubuntu. This is for 9. Okay, just go here. Okay. What it is actually, it is telling that you got this, only what I am highlighting. It is telling that copy files from home tutorials / incompressible folder / simple foam folder / PITZ daily folder. That means if I copy all the maybe tutorials from this home tutorial, in the incompressible folder, simple foam, I should find this particular folder. That's what I'm going to see. Just go here, okay, incompressible. Okay, just go here, simple foam. You can see this, PITZ daily. So that particular, it has, see, I was trying to maybe import only PITZ daily using that particular command. If I use this command, only it would have imported only one folder. But whatever the command I told, cp space r foam tutorial, that means you are importing the whole tutorial folders to your local directory. I prefer you people do that rather doing it every time. So now if you go and look at it, the 2D you have aerofoil, you have PITZ, you have pipe. So lot of things are there where incompressible, incompressible, you have many examples are there. Okay, most of the things will have very similar kind of files actually. Okay. Now we will go to this PITZ daily folder. Okay, if I take any kind of maybe your OpenFOAM folder, it has 3 folders. It has 3 folders. One is called as, maybe here, if you look at it, maybe PITZ daily is the what is called as case directory. That is OpenFOAM case or case study. Okay. Now, if you look at it, 0, constant and system, you have 3 folders. What is the 0? 0 means initial conditions. Hope you remember whenever we are solving FEM problems and all, we used to call as initial condition problems and boundary condition problems. They are very similar to that. Your initial conditions directory is 0. Okay. Now, if I try to open this 0, it has so many things. Okay. It has so many K, U, V, all those things are there. But majority of this actually, the pressure and velocity, you can just open that using your text editor. Say for example, if you go here, open with a text editor, or you can open with a gedit, whatever the way you want. You can just open it, you can see this. This is what you're going to see. If I open this particular P, so it has all the pressure conditions. So OpenFOAM, it has the object is pressure. So dimensions, what are the dimensions of it? Inlet, outlet, upper wall, lower wall, everything. Okay. So this particular thing we will try to discuss. We'll try to discuss what is this. Now what is the, let's try to get comfortable with what are the files it has. Okay. So this is for the pressure. Once it is done, if you want to make changes to it, you can just go and make the changes and save it and you can close it. That's the beauty of this particular OpenFOAM. You exactly know what you have done, what changes you have done. Okay. Now next. If I go to U, you will get all the velocity. Okay, all the velocity is in this particular thing. So what I have given, maybe upper wall, lower wall, no slip conditions. What is the velocity with what is the value? 10 meters per second. Or if I change it to 5 meters per second, if I want to change it to 20 meters per second, you can change. So this value, you are literally checking it, what you are trying to do. So once you are done, once you made some changes, save it and you will close. Then other epsilon is there, k, but most of the things, omega, k epsilon, omega and all. So pressure and velocity is what is most important for us. Other things depends on problem to problem. We'll try to look into it. Okay. So now we'll come back. Now, if you go to your constant directory, you click on the constant directory. Here you have two things: transport properties and momentum properties. Now, if I create a mesh, actually, where it will come to this particular folder with a name called as polymesh, with all the boundaries, faces, okay, points, everything is going to create. Okay, so this is the thing. Say, for example, I have a property new. So just go here, open in the text editor. You can see this. I have a new. So new is nothing but your mu by rho. Okay, it's a Newtonian fluid. So it's a constant 1 e to the power of -5 is what I have defined. Okay, I'll tell about this. What is the 0 to 1 dollar maybe a little later, but I have a value. So I can get this particular value and I can do that. Then if once it is done, you can save it and you can close it. Okay, momentum properties, just click on this. Okay, so all your k epsilon turbulence model, whether I have the turbulence, which model I have used, what a turbulence are they, so what are the coefficients, so on, off and off. So you have k epsilon model, realizable k epsilon, k omega, all these models are this thing. So what model I am using, just I will type here, k epsilon model. If I try to type realizable k epsilon, so that particular thing is going to take. So what model, so this is nothing but your transport or turbulence model I am going to define here. So only two files are here, but other files, once you run it, actually other files also will come into picture. Okay. Let me go back. Then there is one folder called as system folder. Okay, in the system folder you have block mesh, control dict, finite volume, see parameters file. See, finite volume schemes and finite volume solutions, those are called as parameter files. So I can go and click on this block mesh dict. Okay, just click on that block mesh dict. You can see this is nothing but your mesh. Okay, it has all the coordinates. Vertices, everything is going to create it. See, everything is there. Blocks, X mesh, edges, inlet, outlet, lower wall, everything is there. This is for your PITC, whatever the model is, a 2D model. It's a simple 2D model. Look at this, is the source of this particular thing. Okay, once you are done, okay, once it is done, you can close it. Then control dict. Control dict means it's something like I'm going to define what are the parameters, what is my start time, what should be my time step, okay, what is the time interval, okay, what type of, whether it's what type of application, whether I'm using the incompressible foam solver or I'm using a simple foam solver. So all those things, what type of everything I have to type here. See, once you get used to it, no, it will become more and more. You see, it is something like you people have to explore it. Okay, once you start exploring, open for you're using a k epsilon model. So what are the things I need to? So there is a streamline function. Look at this. Everything is C programming. Your open form, if you go and look at it, it is built on C programming. Include. Okay, I'm going to include a streamlines line as a function file. So include a function, user defined function. So I'm using a streamline file and a k epsilon file here. Okay, and I'm trying to run it. This is a simple thing. So when you try to compare two different maybe control dict files, actually, then you will come to know what are the things changes they have done. Okay, so all the precision is up to 6 levels, 6 digits or something. interval, time interval, everything I'm going to define. What is, how many steps you want to do? 2000 steps, 2000 times, everything I can do here. 0 is the starting time and end time is 2000 something. Everything I can define it. Okay, this is about your control dict. Now finite volume schemes, if I try to edit it, okay, just go here. I've taken what type of this thing? It's a steady state solver. Okay, it's a Gaussian linear solver. Okay, then I'm going to look at this particular, what type of schemes I'm using. It's a interpolation, linear this thing. Then the maybe your corrected mesh, maybe what is a gradient? I'm going to use a gradient corrected schemes. Okay, what type of Laplacian scheme I'm using? So this particular thing, I'm see something like you're going to type it. Actually, you're going to look at see all the things are, these are the schemes what is available. Okay, I'm going to use it. What is available? Look at this. This is your finite volume schemes because it's a finite volume solver. Because you exactly know what exactly you are dealing with, and all the some of the libraries are available in your OpenFOAM installed folder. Okay. Then finite volume solution. Okay. Here, what type of solver? Gauss-Seidel iteration smaller, smoother. So what is the tolerance? 1 e to the power of minus 6. I can make it 1 e to the power of minus 5. If I make it 1 e to the power of minus 4, what will happen? Okay, rho u method. Okay, what are the equations? So these are something like you call it as smoothing. So 0.9, 0.95, 0.92 and all. This is something relaxation factors. Hope if you're using the turbulence models, I think this should have, if you're looking into turbulence models actually in CFD, we try to give some relaxation factors so that your solution converges faster. But converging solution faster means that doesn't mean that the solution is stable. Okay, so there is always a difference between a stable solution and a better converged solution. So to play with that, actually, you have some relaxation factors. So that's what we are trying to do. Okay, so this is for the simple algorithm. So these are the things for P, for U epsilon, all those things. Okay, so if you look at it, the solver, so tolerance is 0.1. This is tolerance is 0.01 in 10 to the power of minus 5, and I'm going to use this particular solver. Then close it. So these are the files what is available. These are the files what you have in your system. Now suppose, for example, if I go for a lid-driven cavity problem. Okay, if I go for a lid-driven cavity problem, what I have actually, I will be having different folders. Just go to your incompressible thing, icofoam. Let me go back. Go to incompressible. Okay, incompressible foam, icofoam. You have two. One is a cavity problem, other one is elbow problem. Is that just if you go and click on the cavity, you have all those things. Okay, in this actually you have so many things. So in this you go to this cavity folder. You have once again 0, where you have all the pressure, maybe velocity, those folders. So if you want, you can click on it. Just click on this. Here you see pressure and velocity. If you come back, constant, you have transport, only transport properties. Okay, then click on the system. You have once again block mech, control dict, finite volume schemes, and finite volume solutions. So there are some common for these are some whatever I discussed now. These are the common folders in common files in most of the your OpenFOAM, maybe case, whatever the case study we take now, for that particular case study, these are the things. This is for the incompressible. Okay, so if you want, if you can just go and look into, if you want to look into, okay, so if you go and look into, one minute, let me take this to the side. So now, if you look at it, actually tutorials, you have all the things. I'm looking at only incompressible flows. So most of the things what we deal it compressible. We'll come to heat transfer later. Maybe if you want, you can explore it. Heat transfer, you have buoyancy problem, multi-physics problem, and all are there. Okay, so maybe that people can try. Then maybe some mesh generation, how to generate the block mesh, all those things, refine mesh, all those things. We'll try to do that. So this particular thing is there, how to mesh it. That particular tutorials is there, but we'll try to go with very simple problem, that is incompressible. Maybe we can start with the cavity. Okay, lid driven cavity, we can look into that lid driven cavity problem. Okay, that's a simple example. So that is your maybe what we call maybe a square pipe. It's daily I told, no, that's a square pipe problem, and the lid driven cavity is once again a simple square problem. That's it. So any doubts with respect to this particular thing? You can.
No, sir, clear.
Okay, is it clear? I think most of you had these difficulties now in installing and all. So I think I have cleared your doubts in installation, downloading the whole lot of tutorials. So once your tutorials are there, then these are the files. Opening that file, I think many of you will try to use simple text editor file and open it. Simple things. So I'll just go through two simple problems. One lid driven cavity, I will try to do that, and we'll try to see. We'll try to run this particular thing, and I will show to what and all you are supposed to do. Okay. So just let me go to this icofoam. Okay. Cavity, lid driven cavity. So cavity itself, we have different other things are there. Cavity, clipped cavity, grade cavity, and then we'll discuss later. But simple lid driven cavity we have taken. So now just go here and you can look into this part. What is the this pressure file? What and all is there, and all those things you can look into that. Okay. Now just come over here. You can just open in your terminal. Okay. Just go to. Just I'll come back. Come to this particular thing. Just if you just go and click on the terminal, it will come. This is what you can see in your Ubuntu. Okay, Ubuntu, just go to that particular folder, right click and terminal. So right click and open in terminal, the terminal will come automatically. Now in this terminal, okay, so what is the first thing you have to do? You have to check the block mesh. Meshing your geometry is the first thing. Okay, to do that, we have simple command BLOCK, all small letters. M should be capital, MESH. Okay, enter. Okay, you can see this particular thing. It has started meshing. So just see, simple, you just do it. We'll try to dig into this little later, what exactly it's doing, all those things. Let's go step by step. Now, once you run this particular thing, just try to understand what it is doing. Okay, here I've taken a simple geometry. Okay, I have taken a simple lid driven geometry. That's lid driven geometry means it is nothing but you have a square, this particular thing, you have a rectangular thing, and just like in the top, I'm trying to slide a particular face at some velocity. So inside there is the air. Because of that particular movement, there is a movement of the air in that. So now, if you look at it, how many faces are there? 6 faces. 2 on either side. Okay, 2, 4, maybe 2 on the top side. So side you have 4 faces. Top and bottom 2 faces. So totally there are 6 faces. Okay. Now this is the size, all those things and all. Then it has done the mesh. Okay. Now to solve this, I am going to use an incompressible foam solver. Okay, incompressible foam solver. To do that, actually, the simple icofoam, ICO, look at this. ICO is small letter, F is capital, OAM. So it has converged. Look at this. These are very example problems. So this will converge faster. So as you proceed, as you work on some of the complex problems, these things will come. So that those things you people have to get used to it actually. Once you start using it, your comfortness with the, so it has taken say time step 0.475. If you look at it, maybe in the when I was setting the time parameters, so time step I had given 0.005. You can just verify 0.47, 0.475, 0.48, 0.485, 0.49, 0.495, 0.5. So up to 0.5 it has taken. Okay, that's all the solution. So you can note that the solver has created a directory. See, it has created, now if you go back and see, it has created a directory 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So sorry, 0.5. So 0.1, 0.2, 0.3, 0.4, 0.5. These directories contain the data for that particular time, for that given time. Okay. So for 0.1, for 0.2, for 0.3, for 0.4, and for 0.5, for 5 different time steps. So in between, I'm not writing. Only at 0.1 seconds, 0.2 seconds, I'm trying to write it. So how it will be useful actually, when you go for post processing, I'll be able to do it at 0.1 seconds, 0.2 seconds, 0.2. So I'll be able to create the, maybe your vector plot, maybe your velocity contour for these 5 different time steps. Are you getting? So these directories contain the data for that particular given time. That's the meaning of it. So now I have done this particular thing. Now I have to post. So you have now, earlier when I started the analysis, I had 3 folders. One is 0, constant, and system. Now I have another 5 folders. Look at this. If you want, you can look at this. 0.1 I have. Then look at 0.2 I have created. So I have created 1, 2, 3, 4, 5 different folders after running the solutions. Now I want to visualize it. So to visualize it, see, most of you people try to type ParaView. Okay, if you try to ParaView in the Ubuntu, it will tell that ParaView is not installed. So what you will do, you will try to install that. Don't do that. You type, see, P-A-R-A, para in small letters, and F-O-A-M, parafoam, F in capital, and enter. So what is going to do? Look at this. It's trying to create a cavity.openFoam. Okay, it tells that it's trying to create a cavity.openFoam, and ParaView will open. And ParaView folder will just simply open. Look at this. ParaView, this particular thing is open. Look at this. This is your ParaView 5.6. Okay, 5.6.3 actually, 5.6 actually, which is installed. The 60-bit this thing and all. Now, if you look at it, what is the problem you are considering? So it has written all the data with respect to cavity.openFoam. So what is this actually? This is your data analysis. So data analysis, this is your data analysis pipeline or whatever it may be. Now, once this particular thing, you have to load it. See, this is your case file. Just like if you are using your ANSYS file, you had something called as .cas.dat. You are going to read that particular thing. In a similar fashion, this is your case file only, or analysis file. So just go to this, just below your properties file folder, just if you click apply, the low case is loaded. Look at this. It has loaded the case. Okay. Once the case is loaded, you can see here, it has taken the different geometries. Look at this. Mesh, fixed walls, front and back empty, internal mesh. So these are some boundary things which I have created. Selected the parts of the mesh. So if you want, you can click any of this. So this fixed walls, mesh, and moving wall. These 3 things are important. Other things are not important for me. I have extruded that. Now, if you come little down, your pressure contour and your velocity contour, these fields are ticked in. So this is nothing but I'm trying to load the fields. I'm trying to define the geometry by loading the case file. So you're going to define the case and load it, then define the geometry. So geometry is displayed over there, and what are the fields you're going to see, that particular fields you will be able to see. Is that clear? Okay. Now once it is done, okay. Now if you look at it, there are few things are there. So I'm going to just touch upon which are very, very important. Okay. If you look at it to the left hand side, this is called your plot legend. This is your plot legend actually. Okay. Now this, you see, this is your rescaling the legends. So these are your legends. These 3 things are there now. This is your legends. Say I want to plot something, whichever what you want actually, you just go and click on this VTK block colors, whether you want U or P. So this is your data which you are plotting. Say if I click on U, so it is going to plot your velocity. If I click on P, it's going to play with respect to pressure. Okay, so if you click on this U, okay, this is your U, you are going to see this particular. Okay, now what you are seeing here, this is your time step legend. Look at this. This is your time step legend. What you are going to see. Then, if you go to the top, actually you can see this. The x-axis, y-axis. Look at this. By default, your x-axis to the right-hand side, y is to the top, and z is to the maybe away from you. So this is your default. So whichever direction you want, you can click on it. Say, for example, you want to zoom in and zoom out, all those things. This is zoom to the data, zoom in, zoom out. You can do that. If you want to rotate, you can do that. Say you want to get the orientation of the axis, you can click on this. You want to rotate. So all these things you can try. You want to rotate 90 degrees, plus 90, minus 90, all those things you people can try it. Okay, all the things. So by default, this is what I am going to see this. So fit to the data, and this is the thing that we want to see. So now, see, look at this actually. You have usually either you can go with the surface data or points data, or surface with edges or wireframe. Look at this. I am clicking on the wireframe. Okay, or if you just click on the surface with edges, so this is what you're going to see. You click on this particular thing, only surface will come. So edges are not defined. Mesh is also not there. So preferably most of the times we'll go with the surface. Okay. Now look at this actually, 5 time steps are there. So 0, look at this, how many times? See, once I read the ParaView file, what are the time steps available for me? Look at this. Point 1 is there, point 2 is there, point 3 is there, point 4 is there, and point 5 is there. Okay, for each step. For each step, from 0 is already 0, it's going to calculate. From 0, okay, from 0, point 1, point 2, point 3, point 4, point 5. Okay. If you want to make it more shining and all, you can do that filters, alphabetical, all those things people can do, and you can make it. That you can do. So maybe I'll try to teach you the shining appearance, all those things and all. Just go and sell data to the point and all, sell data to the point, okay, to the point data and all. If you click on it, so it will become more visible, okay. Or if you try with the fillers with the calculator and all will come, or filler data analysis, plot over the line. So those things are extra things are there. If you want to do that, just go to this filters. You can do many things for you. Annotation, all those things you can do that. Okay. Now what we will do actually, we'll try to look into, see, you have this 5 different steps now. I can animate it actually. Just click on this particular thing. Look at this. Simple, I'm going to do this. Okay, look at this particular thing. Once I click on this, point 1, point 2, point 3, point 4, point 5. Point 1, point 2, point 3, point 4. You can see this particular thing. This is a simple driven cavity problem solution. This is how you can visualize. See, this is a simple exercise. This is a simple exercise. What was the aim actually? The aim was, so the aim is to understand what are the files which are existing, how to run the block mesh, how to run the simple solver, and how to take it to your maybe what we call it as maybe ParaView or post processing and visualize it. Say if I want pressure, I can just go and do the pressure also. Whatever I done now, same thing I can do. Okay, just go here, and if you want, I can do this pressure also. I can do that. That's one for the pressure and one for the magnitude. Whatever you want, you can do the coloring, all those things and all you can do. But velocity is preferred, so better to go with the velocity. So stick on to this particular, stick to the window, surface plot and all. You can do whatever. Wireframe is also there. You can do that. Wireframe, surface with edges, anything you want, you can do. When you can visualize it, whatever the simple analysis of your cavity driven problem. Okay. So once you are done, actually, maybe already it's automatically saved. You can just close. Maybe plots you want to export and all, I will teach you how to take the export of the plot and all. Now simple, get used to it actually. Okay, get used to it, what is actually. Now let me go back to that incompressible flows. Okay, we'll go to the simple form. Okay, simple form actually. This is what exactly, maybe PITZ elements a simple, a two-dimensional, some kind of a layer, maybe two-dimensional layer, maybe of particular length and particular width. That's it. It's just like a square pipe is there. It's nothing but a small duct. It's a small duct actually. Okay, here also we have the 3 folders. Okay, here also I have 3 folders. So what I'm going to do, I go on to this particular thing. I will just go to this particular folder. Look at this. Open in the terminal and okay, I'm going to look at this. I will just go and type ls. So I have three folders: 0, constant, and system. Okay, I will just go to your. If you want, see, maybe let me show you the how the block mesh edit will look like. Okay, let me look into that. It's a very simple problem. What you have to do, you can see. I was using directly the edit commands. I'm going to use gedit here. Gedit. Okay, block mesh dict. Okay, where is it actually? So look at this. It is in the system folder. The block mesh dict is in the system folder. So now if I want to run it, actually I have to change the folder to system, or directly I can type cd. Okay, sorry, gedit. Okay, so I am in the PITZ daily system. I have to go to system folder, system slash, okay, blockmeshdict. Okay, block mesh dict is the file name I'm trying to give. Press enter. See, this is what you're going to see. This is what you're going to see. Your block mesh dict is the file actually. That's the object. And everything is so. This is where it is. The file is a copy is in. So the form tutorials as this particular block mesh. In this particular thing, it is there. Now look at this actually. Now convert to meters. What is this actually? That is your scaling factor. Okay, I am going to convert from millimeters to meters. 10 mm to maybe this particular thing. If I want to convert it to meters, I have to divide it by 1000. So the conversion to meters is 0.01. So the conversion is 0.01. That is your scaling factor. Okay, that is your scaling factor. Okay, now what are these vertices? Vertices are the location of the points x by z. Look at this. Minus 20.6, 0 and minus 0.5 is the first point. Minus 20.6, 25.4, minus 0.5 is your second. So those are vertices point locations. Okay, those are vertices point locations. So all the vertices point locations are given here. Okay, with negative, positive, all those things are. Now if you come down, okay, if you come down, you have something called as blocks. See, blocking division is along the axis, x-axis, y-axis, z-axis. 1831 XYZ. Okay. Now, how many? See, if you put X this thing, and you have some points 0, 3, 4, 1, 11, 14, 15, 12 points needed to build the block. That is the meaning of it. What does it mean? See, example, it's something like this. I'll show this. Try to open the. See, usually we'll move from back to first. 0, 1, 2, 3, the bottom one. Okay, then we'll go in the clockwise direction. We'll go in the clockwise direction. That's how things will work. So 0, maybe something like a bottom most, say we have a ground floor. The bottommost layer is actually moving in the clockwise direction. It is 0, 1, 2, 3, 4. That's the meaning of it. Okay, 0, 1, 2, 3, then 4, 5, 6, 7. That's the meaning of it. I'll show that. Okay, now try to have a lock. Okay. Look at this. I have one block here. I have one more block here. Okay. I want to join this block. Can you see this? I have a line from this point to this point. Okay, fine. Now, insert the text. Okay. Now, how it goes actually? Now, this is your 0. Okay, bottom line. Then, this is your 1 at the bottom. I'm going to take a right turn clockwise. Okay. Then, I will go here and this is your 2. This is your 3. Today I forgot my iPad. That's why I have all this difficulty. Otherwise, I would have gone to my iPad and shown. I left it at my home. See, look at this. At the bottom, I have 0, 1, 2, 3 actually. Then I can go with the same thing. And at the top, this will be my 4. Okay. Then this will be my 5. This will be 6. And this will be my 7. So now you got an idea what it is actually. 1, 0, 1, 2, 3, 4. It starts with 0. 0, 1, 2, 3. So now if you look at the axis, maybe x-axis is along this direction, 0 and 1. That means in this direction, x-axis. In the 0 and 1 direction, I have x-axis. In the 0 and 3 direction, I have y-axis. So that means 0, 1, 2, 3 is the xy plane. That's the meaning of it. Now, this is 0, 4 is your z-axis. Now, exactly at this particular point, I can have a symmetry. So exactly between this particular plane, I can have a symmetry plane. So symmetry plane is nothing but, so you are exactly at the center, and these are your walls. 1, 2, 3, 4. You have 4 walls. So you have a wall, you have a symmetry plane, you have all the points defined. Is that clear? So points. So now, if you go back and see this particular block mesh dict and all, so definition is 0, 3, 4, 1, 11, 14, 15. That means I'm dividing more number of points. Okay. But how the numbering is done? Numbering is done that particular fashion, whatever I told. Okay. Now, see, this is nothing but your division grading. See, this is in the position y, negative y. So that means, as I told, see, if I say, for example, if I define this as 0, 1 as a positive x, if I go in opposite direction, it is positive or negative x. 0, 3 is a positive y. If I go in opposite direction, it is negative y. 0, 4 is positive z. If I go in opposite direction, it is called negative z. So that's how the grading will become. So positive x, positive y, and maybe your r. So positive y and negative x and negative x. So that's how the negative directions will come. Negative x, positive x, and positive y, whatever. The positions is going to define it. It's going to be it as defined in that particular fashion. Okay. Now, then they're given some edges, the boundary. So inlet, that's the top one. That's called as a phase. So if I define it as an inlet, that is the name of the phase. Okay. Now, what type it is actually? Phase type, and see, this is your name of the phase name. Inlet, outlet, upper wall, lower wall. Okay. Now, what is this actually? That particular boundary 0, 1, 12, 11. So that is the point. So it consists of that particular vertices, that points. So those are 0 vertices, 1 vertices, 12 and 11. That forms your, so bottom, see, as I told, so you have bottom one layer, then one layer, then one layer. So 4, 5, 6, 7, 8, 9, 10, 11. That means it has divided into that particular fashion. So that's what it's telling. So many faces. So I have divided into so many faces. So top wall, then it has the upper wall, it has this particular faces. So this is one face, this is one face, this is one face. So lower walls, it has defined. So all the points, so they are in particular sequence. They are in the particular sequence. That's the meaning of it. Is that clear? So once that is done, actually, this is how the that particular thing is done. Maybe the naming and all. So what you have to do, you have to just go to this terminal, go to the terminal and just type block mesh. Okay, just type BLOCKMESH, block mesh. It has defined the meshing. See, sometimes actually we may have to look at the mesh, what it is actually. So you have an option, I think, just like in your ANSYS Fluent, you have checked mesh checking. So here you have the simple command CHECKMESH. I can just check for the meshes. What does it do actually? The moment I type that particular thing, so it's going to tell, okay, it's going to tell how many points are there. See, some of you might have done your PFD analysis. In that actually, how many faces are there, how many points are there, all those things if you want to get it, no? How many cells are there and all. If you want to get the details actually, just type this check mesh. How many boundary faces, how many points. So cells, look at this, it's around 12,225. So how many exact, so all are exact, so there are no prisms. So it's purely an X mesh. Okay, whether all the boundary definitions are okay, whether all the things are fine. So then you'll be getting it. So you have 1, 2, so inlet, outlet, upper wall, lower wall, front and back. So you have 6 faces. Okay, then everything you will be, it is nothing but checking your mesh details. Checking your mesh details. So just simply type check mesh, you'll be getting it. Okay. Now, say if I want to look into the turbulence properties. Okay, there the turbulence properties will be there. The turbulence properties, as I told, like maybe K epsilon or K whatever is there, it will be in the constant folder. Okay, just go here, look at this particular thing, turbulence properties. Say for example, if you want to, so turbulence model specified in the turbulence properties. Okay, turbulence properties or transport properties. So those things will be there in your that particular thing. Fine. So whatever polymesh I created now, all the points, neighbor, faces, everything, it's, I think after I ran that command actually, this thing got generated. This thing, this particular mesh was maybe written. I think this number of files were written. So simply you will just type turbulence properties. Okay, you just type this particular thing, turbulence properties. So usually your epsilon, K epsilon, omega, all those things, as I told, maybe in the some of it, maybe if you go to this particular thing, look at this particular thing. So all your files, your turbulence property files and all are written in this particular system. In the constant folder, all your, maybe sorry, 0 folder actually, that is your initial this thing, all your files are here actually. epsilon k and all, they are defined here. Okay, that means if you go to constant, in that actually I've seen couple of files where folders where you will have a separate file called as turbulence properties. Turbulence properties itself is a file where all your k omega and all will be defined, and you will be using that also. So that option is also there, or you can just go to this particular 0 folder and you can check for it. Maybe if you go and check for your P file or P file, already I've shown you P file, it will contain your dimensions, it will contain your what type of gradient, boundary conditions, or physical field, all those things. Maybe let me go and check it, look at this. Okay. Just click on the P file. So this is what you will be able to see. So this is your physical field. So physical field is object. This is your object is the physical field, and the unit actually. If you look at this particular thing, this is your dimensions. So then initial conditions. Okay. If you look at the internal field, this is your uniform. This is your initial conditions. It is 0. Okay. Then the boundary conditions. All the things are inlet, outlet, upper wall, lower wall, and front and back. Okay, all the velocities are defined here. If you want, you can see, maybe to begin with, actually, you can take the particular file, you can do that. If you want to change it, actually, you can change a particular value. Maybe I told the 10 meters per second something I'm going to define. You can change it to 5 meters per second or whatever it may be. Those things you can do. You can change it to, or if you want, you can change the boundary field. So this particular value, no. So instead of 0, you can make it 0.005, 0.01, something like that, and you can do that. All those things you can change it. Maybe at the inlet conditions, you can do that. You can make it a uniform, and you can do that. You can make some modifications, and you can do that. If you do that, actually, your corresponding control dict will have the conditions. So control dict will have the conditions of that particular thing. Okay. Once it is done, is a simple, maybe what we call it as incompressible fluid analysis. Just you have to come to that particular folder, cavity PITZ folder. What you have to run actually. So it was an incompressible maybe solver, previous one. Here it is not a, you see here I'm going to consider the turbulence model also. So it's a simple foam, simple in small letters, FOAM, simple foam. Okay, just run it. It should maybe roughly depends on how many iterations. So sometimes it may take 100 iterations, sometimes it may take 20 iterations, sometimes it may take 30 iterations, depending on how you define the converters. Here this is an what example for around 30 iterations you should convert. Around 25 to 30 iterations you should be able to convert. Otherwise, you will take more time to convert. I think it has taken roughly 280 iterations. Okay, simple solution is converge. So it has converged and I got the solution. To visualize this particular thing, what should I do? Just go here, type para foam. Okay, so it's trying to create that particular thing. Okay, just go here, click apply. See this particular thing. Let's come. This is a simple model I have. Okay, maybe here also you can just go and look at the filters. Filters you can slice it. You can use the slice option is also there. You can use this option, or if you want to do some data analytics, that also you can do. Something went wrong. Okay. Now, say for example, I want to plot with U or V or whatever you want. You can just go here and you can just do that analysis. You can look at this. It has 100, 200, and 287. You can look at this particular. This is how you can do the simple analysis. Zoom it. and you can see. Yeah. So ensure that you have at least 4 GB of RAM to do the simple analysis. The simple thing. Now, what I want is actually maybe today or tomorrow, you people just try to install this OpenFOAM on your machine and get used to this files. Get used to these files actually. Simple files and all. Then we'll come back to and see that what type of maybe heat conduction problem or pipe problem or aerofoil problem, those things. We'll try to look into that. You can take any kind of aerofoil, maybe symmetrical or this thing. You can do that and you can do the meshing all this. Yeah, anything? Anything you have doubts?
No, sir, but we have to practice it once.
Yeah, no, it comes easy. If I'm able to tell this so easily means, so it has taken for me also. Yeah, if I put yourself in my footsteps, it has taken so much of time for me also to learn this. It has taken years sometimes because at least no one was there to teach me at that time. So everything I have to depend on simple, maybe what we call it as spoken tutorials or